In this video, I want to talk about geometric sequences and what the limits of geometric sequences are. A geometric sequence is of the following form. The general term of the sequence is a times r to the n, or a times r to the n minus 1, depending on how we've determined that first term, whether or not we can see the common ratio appearing in the first term, where a and r are both fixed real numbers. And here in my notation to start out, I'm making the assumption that we start out with n equals 0 or 1, but this can be adjusted so that n would start somewhere else. I would note that r, this number we're multiplying by at each step, is called the common ratio. It gets its name because when you take one of the terms and divide by the one that comes before it, you can notice that that ratio of sequential terms is r, so that every term in the sequence we multiply by r an additional time. So here to start out with, I've drawn the example of the sequence where I have let a, that coefficient in front, be 2, and my r is 0.9. And we can see that with each sequential term, the value of the sequence is shrinking. We start with 2, but each time we're multiplying by a power of 0.9, because 0.9 is a number smaller than 1, then this is behaving more or less as a transformation of e to the negative x as we approach positive infinity. So we're multiplying by something less than 1, which continually scales down the size of the value of the terms of the sequence. And as we move along, we end up getting a value of limit 0. So ratios raised to the nth power when that ratio was less than 1. Having limit 0, that's something I want us to have sort of internalized. So we can see that when r is less than 1, I can change a here. A can be positive, a can be negative. That multiplier won't change. The key thing controlling the behavior of this geometric sequence, in particular its tail, is the fact that r here is a positive number less than 1. Let's see what happens when I make r a negative number less than 1. Let's try negative 0.7. So when we look at negative 0.7, we can see that positive powers, so here's the first term, or the second term, so we see that even powers produce negative values and odd powers produce positive values, or scratch that, reverse it. Even values produce positive numbers. Odd values here are producing negative numbers, because when I multiply by a negative number to an even power, the negative signs cancel out one another and we end up with a total value that's positive. So we see this sequence is bouncing back and forth, but it's centering down on 0. And applying a theorem I have, there's a theorem that states, and this is one of the ones you found in the text, that if the limit of the absolute value of terms of a sequence approaches 0, so converges to 0, then the original sequence must also approach 0. And I can obtain this result via a squeeze theorem argument. If I know that the absolute value of my sequence, here I'll type it over here in this document, if I take the absolute value of my sequence, it's the absolute value of a sub n, and I know that the limit of that sequence is 0, so a sub n goes to 0, then negative 1 times the absolute value of my sequence terms must also shrink to 0 as we go to infinity. And whatever a sub n is, it'll always be between the negation of its absolute value, so where every term is negative, and the absolute value itself, where every term would have been made positive. So I have these three sequences, and I can create the following inequality. Negative absolute value of a sub n is less than or equal to a sub n, which is less than or equal to the absolute value of a sub n. I'm going to circle this so we can see it better and make it into pretty notation. So here we are. This is the result we're talking about. Because I've got this sandwiching going on, it is through this process that I can prove, since I knew that when r was positive but less than 1, the limit of the sequence shrank to 0. That provides me with an algebraic proof that when r is less than 1, when the absolute value of r is less than 1, I'll get the same result. Notice that r equals 0 would be a specific case of this. When r equals 0, if I set r to 0 here, we can see we really are getting the sequence that always spits back 0. So we understand the results when we're between -1 and 1. Let's next look at what happens at 1. We're talking about a times 1 to a power. Well, whatever a times 1 is a, and so that's going to determine the value of this sequence. So when r is 1, I'm going to get back 1 or a times 1. So what about -1? -1. Well, powers of -1 alternate from having value +1 and -1. This is a classic oscillating divergent sequence. No matter how far I go out in the sequence, I will still have every other term being +1 versus -1. Since those numbers are not close together, I can't send an epsilon such that every term is close to one or the other. Then I'd conclude that the limit of that sequence is a divergent by oscillation example. Similarly, if I let r be any number less than 1, we're going to have the same divergence happening here. I want to have it where you can see it really well. So I'm trying to get the value kind of not too big so you can kind of see it. So it's spraying out like this, bouncing back and forth but getting farther and farther apart. So we still have divergence as long as r is greater than 1. Then since the absolute value of r will be heading towards infinity, the even terms heading directly to infinity, we can see that every even numbered term heads off to infinity. The odd number terms are heading to negative infinity because they're the negation of a positive sequence where the magnitude grows to infinity. And so we have divergence as long as r is less than or equal to -1. And then the last case is when r is a positive number, greater than 1, and you can see here these grow off like typical exponential functions. We know that when the base of an exponential function is a number greater than 1, its derivative is going to be positive, and if the derivative of an exponential function is positive, that indicates it's increasing. So we've got an increasing function that's increasing without bound. Every single derivative of it will also be positive. So it's increasing at an increasing rate. This thing is growing forever, so the limit will also be infinity. So we have divergence. We only have convergence when it's equal to 1, and we're going to converge to that a value. And then when we're between -1 and 1 for that ratio, we'll get a value of 0. So, to conclude, this is the theorem on the convergence of geometric sequences. For a geometric sequence of the form a times r to the n, let's assume we start n at 1, then this limit of this sequence converges, the limit is 0 when r is between -1 and +1. If the ratio is 1, then the limit will equal a. The limit will be infinite for positive a value when r is positive, and negative infinity if a is negative but the ratio r is positive. And then for any case where r is less than or equal to -1, we have that this geometric sequence will diverge by that oscillation, the fact that the positive terms are not the positive terms, the even value terms will be heading in the same direction as a but to infinity, and then the negative terms will be heading in the same direction as a but to negative infinity. So there'll be this opposite. Every other term will head to plus infinity versus minus infinity, which forces the sequence to diverge by oscillation.